we learned that with the duobinary pulse, we can transmit message symbols at the rate of 2 B samples per second, where B is the bandwidth of the channel, but this introduces controlled ISI. Now, we saw that this is the block diagram for a output of a duobinary pulse generator. The input bits are IK and the output sample values here YKTB or BK is given by this relationship alpha k plus alpha k minus 1, where alpha k are the polar conversion of the message bit Ik. For Ik equal to 0, we get value to be minus 1, and for Ik equal to 1, we get equal to plus 1. Now, we saw that for alpha k plus 1 minus 1, this gets mapped to Bk for to minus 2, 0 or plus 2. So, whenever we receive minus 2, we know that the input message bit has been 0, and whenever it is plus 2, the input message bit is plus 1. But whenever we receive 0, then the detected bit at that instant is dependent on the previous detected bit. So, if the previous detected bit was 0, then the current bit will become 1, and if the previous was 1, it will become 0. So, what this implies that if there is an error in the detection of the previous bit, then there will be a cumulative effect on the error till the arrival of the next correct minus 2 or plus 2 value. So, we said, is it possible for us to relate this Bk directly to the message bit Ik? And this can be done as follows. For just presume that we do some kind of processing on this message bit and generate another sequence of message bit, let us call it as Bk. This Bk message bit is related to the input message bit Ik and the previous values of Bk. So, my Bk, let me assume to be a function of my message bit Ik and Bk minus 1. If I assume this, then I can write my, at this end, remember my alpha k now would be equal to twice Bk minus 1, because the input to this at this point will not be Ik, but it will be Bk. So, I get this, and then your beta k would be equal to alpha k plus alpha k minus 1. Right? So, this I can rewrite it as 2 Bk plus Bk minus 1 minus 1. So, what this implies that my Bk plus Bk minus 1, this would be equal to Bk by 2 plus 1, right? And this will be modular 2 addition. Okay. So, we want that this should be Bk should be directly related to Ik. So, we want that your Ik should be equal to Bk plus Bk minus 1. So, this implies that your Bk should be equal to Ik minus Bk minus 1, which in modular to arithmetic is nothing but ik modular 2 addition bk minus 1. Subtraction and addition would be same for modular 2 arithmetic. Okay. So, if we do this now, then I will get the block diagram for my duobinary pulse transmission as follows. I have my input ik, then it passes through this block out here, which is nothing but the modular 2 addition of ik and bk minus 1 to obtain bk, and then there is a polar conversion to alpha k, and then this is your duobinary pulse generator. Remember, bk is same as yktb, right? Fine. So, this relationship would be satisfied. Now, if you look at the truth table for this, we can write down the truth table for this very easily. Ik bk minus 1, I have bk, and then beta k, which is nothing but equal to y of ktb. So, when this is 0 and this is 0, exclusive of would be equal to 0, and bk would be equal to minus 2 corresponding to the polar value of this 2, then I will have 0, and if this is 1, this will become 1, and then this will become plus 2 polar values of this 2. So, then you have 1, 0, this would again become 1, and this becomes 0 polar value of this 2 bits, 1, 1, this is 0, again this would be equal to 0. So, from this we see that from here also it is clear that your bk is nothing but ik modular 2 addition with bk minus 1. And we see that in this case that your 0 gets mapped to minus 2 or plus 2, and 1 gets mapped to the output value 0, correct. So, if we find out the conditional PDFs for this, remember these are all Gaussian signals, right. So, if we take a conditional PDF, the conditional PDF would look something like this. This is the conditional PDF which I will get for yktb, given that I have transmitted 0t, that is transmitted value is 0, I will get it either plus 2 or I will get it minus 2. So, this is the conditional PDF for this, for the output, given that 0 has been transmitted and given that 1 has been transmitted, 1t denotes 1 transmission. This is the Gaussian PDF which I will get. So, 0 and 1 are equiprobable. So, if 0 and 1 are equiprobable, it is easy to see that this intersection points are going to decide your decision boundaries. So, whenever the output, this is your output yktb, whenever this quantity lies between minus 1 to plus 1, decision will be in the favor of 1. So, 1 will be decided, 1d means the detected bit is 1, and similarly 0d means the detected bit is 0. So, whenever the mod of yktb is greater than 1, I decide in favor of transmission 0d. So, I will get this form, fine. Now, given this, let us try to evaluate the performance of this duobinary pulse and compare it with the 0 ISI pulse. So, here in this case, please remember, without loss of generality, we have considered a to be equal to 1, because your alpha k for 0 bit I get minus 1 and for 1 bit I get plus 1, but it could have been for 0 bit I could have chosen minus a, and for 1 bit I could have chosen plus a, and this figure has been drawn considering that, but for our discussion we can assume that A is equal to 1. In this case, please observe that probability of YKTB equal to -2 and probability of YKTB equal to +2, they will be totally is half, because probability of 0 being transmitted is half. So, the probability of this occurrence is 1/4 and the probability of this happening, probability of YKTB equal to +2 is 1/4 and probability of YKTB equal to -2 is going to be 1/4, and probability of YKTB equal to 0, correct, will be equal to half, because probability of transmitting 1 is half. So, now we have to calculate the probability of errors. Now, this probability of errors can be easily calculated. Look at this areas which I have indicated. Area 1 denotes everything below this curve from this point onwards right up to infinity. Similarly, 2 denotes the area under this curve right up to the infinity. 3 denotes from this point right up to minus infinity. This will be plus infinity, this will be minus infinity, and similarly here for area 4, from this point onwards the area under this curve right up to the plus infinity. Now, as far as the probability of error is concerned, approximately, as far as 1 and 4 are concerned, correct, that is the error which will occur when I have transmitted 1. So, anything lying here or anything lying here would go in error. So, this probabilities I can find out, this would be equal to sum of this plus this multiplied by half would be the probability area under this curve. As far as probability of wrong detection, that is pertaining to 0 being transmitted, is the area under this curve from here up to this point, and for this point it is from here up to this point, correct, but we will approximate it, correct. We will assume that this area from here up to this point is same as going from here up to minus infinity, and here also from area under the curve going from this point to this point is same as going from here up to plus infinity, correct. So, if I take that, then I can write down my error as follows. So, this is we mention equal to 1/4, because total is half and the probability of YKTB is equal to 0 is equal to half, and probability of error is approximately equal to, remember there is approximation involved here and there is approximation involved here for the area 2 and 3, correct. Therefore, this is 1/4 and this is also 1/4, correct. Whereas this is this areas 1 and 4. So, I get this, correct. Now, this is simple, it's simple to show that this quantity area under these curves, we have done it earlier. So, it is going to be 3 by 2 q A by square root of the variance of the output noise, right. Now, this is the noise variance at the output of the receive filter. Now, please recollect that we are using the same model at which we had used for 0 ISI. So, we have a input stream here and it passes through transmitting filter channel. On the channel we have Gaussian noise with 0 mean and we have a receiving filter. The only difference is now here that product of HTF, SCF and HRF should be such that we get PF to be duobinary pulse rather than 0 ISI pulse. That is the only difference. And so, again we will see that we want to choose SCF is assumed to be fixed, So, again the transmitting filter and the receiving filter, which are also known as terminal filters, are chosen to maximize this quantity because the error turns out to be proportional to this quantity. Right. So, Q is a decreasing function, so I have to maximize this quantity, and the constraint is that PF should be the now dual binary pulse and the transmitted power level is fixed. So, if we assume this, let us try to compare the performance of the dual binary system with the 0 ISI system. So, we will assume that over the frequency band of interest, SCF is equal to 1. White Gaussian noise we assume with a power spectral density given by italic n by 2 watts per hertz. Okay. So, for the binary pulse amplitude modulation with 0 ISI, we have derived this in the previous class that this ratio maximum will turn out to be this quantity, right? And PF would satisfy the condition for 0 ISI, right? That is important. So, now in this case we will just try to let us find out what is this ratio for the case when we have the white noise and this to be equal to 1. So, if I just plug in that values, it is straightforward. I get this quantity, SCF is equal to 1. So, this is equal to this, I get this quantity. Now, remember that integration of this quantity would be equal to 1. We have seen this because PF is equal to HTF multiply SCF multiplied by HRF, right? And PF being real, so mod is also real, and the integration of PF over the frequency range will give you PT at t equal to 0, and that we have chosen equal to 1 for 0 ISI pulse. Therefore, this quantity will turn out to be 1. So, this reduces to this expression out here. Correct? So, probability of error now would be given by Q of this quantity, we have seen this earlier. Right? So, this is equal to this is for 0 ISI. Okay? Now, let us see the same thing what happens when we have dual binary pulse. For the dual binary pulse, again we will be required to evaluate this quantity A squared by variance of the noise at the output of the receive filter. The maximum value will, the expression will remain the same. The expression is the same one without any changes. Here also now again we will assume to be the white noise, constant 1. PF will be chosen to be a dual binary pulse, that is the only difference, correct. Otherwise this expression remains the same. Okay. So, here we integrate. So, for the dual binary pulse, this is the expression for the PF, this we have done in the earlier class, and if I integrate this quantity out here, I will get sine of this quantity divided by pi TB, evaluate over lower limit and upper limit, straightforward. I calculate it, I get equal to this quantity, correct. And now we plug in this quantity into the probability of error for the dual binary case, which we have shown to be 3 by 2 multiplied by Q of the square root of this quantity, fine. And this quantity, square root of this quantity is the square root of this quantity. So, fine. So, if we do that, I get the probability of error for the dual binary case to be equal to this value, fine. Now, we can discard this factor of 3 by 2. Then the above result implies that for a duobinary system the transmitted power must be increased by 4 by pi squared, or in terms of log this turns out to be 2.1 dB, to achieve the same probability as 0 ISI system, because I want this term to be the same as I get from my zero ISI system. I want this term to be the same as the term here. So, I have to multiply this by power, I have to multiply it by 4 by pi squared. Okay. Fine. Now, we have seen that duobinary pulse gives us sufficient amount of power around DC. It is a cost function. So, many times we have communication channels which are AC coupled to prevent the DC from being transmitted or prevent the slow drift of DC. In such cases, we require the PF also to be of the same characteristic, in the sense that it should have a null around 0. Now, this kind of channels, example would be telephone channel or magnetic recording channel. So, how do you generate the pulse which satisfies this requirement of providing a null around DC? So, this kind of thing is known as what is known as modified duobinary signal. So, if we take the sampled values of the PT to be equal to this, P0 equal to 1 and P2 be equal to minus 1, and this is equal to 0 for all other k, then I know that I can, this is known as the pulse which we will get from this, I will call it as modified duobinary pulse, and it is indicated by MD. So, it is easy to see that the difference between that pulse and the pulse corresponding to 0 ISI would be only at for this value, correct. So, we can see that this can be generated from my PMDT can be generated from my 0 ISI pulse using this relationship. It is similar to what we did earlier for the duobinary pulse. So, if I do this, basically it is straightforward to show that the frequency response of this is equal to this quantity, simple, using the Fourier transform properties, and this can be simplified by removing e raised to minus j 2 pi ftb outside the bracket, and you can show that this expression turns out to be this. And from this we can immediately even write down the time characteristic of the modified duobinary pulse, and this would be equal to this quantity out here, which if you simplify turns out to be this, correct. And if you look at the Fourier spectrum and the time domain characteristic of this modified duobinary pulse, they would look something like this. So, we have a null at 0, this is the amplitude response of the PF, and this is the phase response, and this is the time domain thing for this. And then we can easy to say again that I can, my duobinary pulse generator, this would be modified duobinary pulse generator, would be given as shown on this slide. Again you will get these values. From here we see, like what we, the same argument which we followed for the duobinary pulse, we can see that whenever Bk is equal to 2, the present transmitted bit has to be 1, and if it is minus 2 it has to be 0, and when it is equal to 0 I have that the current bit is the same as the bit detected 2 bits previous to this, because now we are involved with 2 TB, correct. That is the only difference, correct. So, Ik would be equal to Ik minus 2. Now, again the same problem, if you make a decision error, there will be a cumulative effect on the error. And so, if you want to get rid of this, it is simple again to see that I can do some kind of pre-processing on this and get my Bk such that, so my alpha k is again same as 2 Bk minus 1, my beta k in this case is going to be alpha k minus 2, correct. So, this you can show if I use this is nothing but Bk minus 2. So, what this implies that Bk minus 2 would be equal to Bk by 2 modular 2. So, this we want to be equal to Ik. So, this implies that my Bk is going to be equal to Ik plus Bk minus 2, which will be equal to, this is modular 2 arithmetic. Okay. So, similar thing. Right. So, if I do this, I will get my block diagram for the precoding of Ik. This is also known as differential coding. So, instead of transmitting Ik directly, you do this kind of precoding, which is known as a differential encoding or differential coding, and then transmit, correct. If you look at the truth table for this, we can easily generate. So, you see that for both 1 can get mapped to either plus 2 or minus 2, and 0 gets mapped to 0. Right. So, in this case also you see that the performance of this system would be inferior to 0 ISI by approximately 2.1 dB, because more or less the PDF, conditional PDF figure what we saw earlier for the case of a duobinary case will remain the same. So, you will again, ignoring that factor before q, the thing would be almost more or less same, correct. Okay. Now, this binary pulse amplitude modulation can also be extended to Emery pulse modulation using the duobinary pulses. We will not go into those details at the moment, but it is possible to do that. Now, remember that we have designed all these pulses and the transmitting and receiver filters based on the assumption that my channel filter remains fixed. But in a practical scenario, this channel filter SCF could change, or the receiver is not aware of the channel filter. If the receiver and the transmitter are aware of the channel filter, then it is possible for us to incorporate in the design of a duobinary pulse or 0 ISI pulse. This we have seen earlier, right? That is design of optimum terminal filters. But in the case when SCF is not known, then in that case, if you take, even if you have designed your filter for 0 ISI, you will get ISI, because the filters will not be matched now. PF value will not satisfy the Nyquist criterion for 0 ISI. So, in such a case you will have to do some type of a signal processing at the receiver end and try to remove this uncontrolled ISI. Duobinary pulse and modified duobinary pulse gives rise to control ISI, which we can take care of at the receiver. But this, because of the unknown information about SCF, this will give rise to uncontrolled ISI, and we will see how to take care of this uncontrolled ISI in practical scenarios, and this we will do it next time. Thank you.